Margin with 23650 MillburnX here today at the New Jersey State Championship. After an outstanding season, they're going to talk a little bit more about the robot today. Now, if you guys like to start off by introducing yourself.
Hello, I'm Alexandra. Hello, I'm Akshara.
Hello, I'm Eric.
Hello, I'm Kadar.
Hi, I'm Mac.
Your outtake here, it's very unique. You guys use Go Build a Viper slides, it looks like, that are belt driven. How's that really working out for you?
Yeah, so earlier in the season, we used Misumi slides with stringing, and that ended up being pretty inconvenient for us because the string would snap and we'd have to restring it often. So we decided to go to Go Build a Viper slides with belts to be more consistent and reliable.
Awesome. Yeah, so you have a hang mechanism over here too. Can you walk us through that?
So our hang mechanism is these two Delrin hooks, and then we can just use the same lifts used to score to hang because they're mounted to the Go Build a Viper slides. Initially, they were pointing upward, but we realized that didn't give us enough lift off the ground, so we slanted them downward to help with that.
Cool. So now let's talk a little bit about your outtake over here. You have rubber bands to kind of give grip, I think, or how does that work?
Yeah, so definitely we had experiences with dropping samples we were trying to score in the past, so we made sure to put rubber bands there to help with grip.
So talking a little bit more about your intake here, I see a differential right here. How did that help you in this season?
Yeah, so we made the decision to add a differential gearbox about halfway through the season. We opted to use these Go Build a bevel gears because we didn't want to deal with 3 printed gears not meshing correctly and snapping, so we opted to use these Go Build a gears. We have these axons here that allow us to track the position of the claw. This way our claw can rotate up and down and side to side, which we combine with computer vision in order to rotate to automatically pick up samples from the submersible. Additionally, our entire arm can flip up and down so that we can go into the submersible, have our arm flip down, then we can flip back up to get into our transfer position.
Really cool. So now let's talk a little bit more about your drivetrain and how your drivetrain works and really what makes it unique.
Okay, so here our drivetrain is powered by 4 motors, and each mechanism wheel is powered by belts connected to the motors. The reason we chose mechanism gears is that we will be able to strafe left and right. And as you can see, these aluminum side plates here, we chose aluminum because it makes the drive sturdy, and the holes you see here are the pocketing that we made to reduce the weight of the robot.
How did you guys use weight reduction throughout your robot? I see you guys use pocketing, especially in areas like these in your outtake and your drivetrain. So how did pocketing really become something that you guys wanted to use?
Yeah, so before our league tournament, originally all of these metal parts that you see now were made out of Delrin because this allowed us to prototype easily, and we have an in-house laser cutter that we use. However, before our league tournament and before states, we decided to send out for metal parts because we were able to shave off about 5 pounds from our bot by pocketing the aluminum. And all of these white pieces that you see are powder coated aluminum. Same thing on our outtake arm, our intake, as well as our side plates are all aluminum, which allowed us to save a lot of weight off our bot.
Cool. Now let's talk a little about your programming. I see you guys have a Logitech camera over here. How would you guys integrate your sample detection along with the automatic alignment you guys showed throughout your matches?
So we have an auto pickup system using this webcam. So what we do is we first scan it downwards and look at the current layout of the samples. We take one picture, and using that, we use our trigonometry to basically determine the shape and position of this using a color mask, where we essentially look for a single color on the entire image capture. For example, if we are playing on the red lines, we'll only look for red samples. This way we can determine its exact position relative to the robot's camera. Using that, we can then calculate exactly where we need to move using the odometry, and we can then efficiently pick up. And this has saved us a lot of time in Telya by eliminating both driver error and saving just the amount of time needed to adjust our position.
Awesome. Yeah, so your autonomous pathing, how'd you guys implement your autonomous pathing? Do you use things like waypointing? And if so, how do you guys implement those types of techniques?
Yeah, so this year we use 2 different things. We use FTC's command-based system as well as a custom control library called R-Control. It has 3 different algorithms: PID to point, peer pursuit, and guided vector fields, and we use a combination of throughout the system. We also have custom TUI, pass every TUI, and stored in a file format that can be either hot reloaded onto your robot or uploaded while offline. And we also have a physically accurate robot simulator to run through.
That's awesome, yeah. So thank you guys today again. We're here with Team MillburnX 23650, and after an amazing season, they talked about the robot to us, and thank you guys for having us with you guys today.